All right, hi everyone. We'll get started. Um, so welcome. Your exam is tomorrow at 11:30 during class. So you just have to show up and take your exam, and then that's it for tomorrow. It should be, I think, like 16 or 17 questions if I remember correctly, and you'll have the full class time to do it. Are there any questions for me about the exam in terms of logistics? And then the seating chart is on Canvas as well. If there's no questions about the exam, then I can just jump into questions on content and stuff. I pulled up the practice exam in case there's any questions on that. But you can ask anything in general that you would like to see as a review. And feel free to take yourself off of mute or just use the chat. I don't have a preference. So we did go over intermolecular forces at the review session on Wednesday. So if you look back on the resources page, you can see intermolecular forces in terms of like breaking that down. So, but in case you have any issues on that, we kind of break through all of the different intermolecular forces. But just remember that these happen like between you can either happen between the same molecule or between different molecules. So just make sure you're looking at um what the question is asking for. Usually it'll be just between molecules. Um Number 4. Yes. So for number 4, wait, we have based on the photoelectric effect, Einstein proposed the idea that and right, you have to decide like true or false statements based off of what the photoelectric effect told you. So remember that the photoelectric effect was that we had a wave come in and then an electron bounced off. So for part A, or for answer A, we have the energy of a single particle or photon of light is inversely proportional to its frequency. Um, we have to, right, you can true or false this as well. So we have a couple equations. We know that energy is equal to h times frequency. These are direct relationships. So as energy goes up, frequency goes up. So this is false. So even though that since that's a false statement, it can't be true. The wavelength of light is inversely proportional to its frequency. We know that the speed of light is equal to wavelengths times its frequency. This is a true statement, but this is not what we learn from the photoelectric effect. So yes, as you increase wavelength, you decrease the frequency. That is true. They do have an inverse relationship. But that's not what we learned from the photoelectric effect. We learned that from like just the speed of light. So B is incorrect. Particles can show characteristics of wave under certain experimental conditions. So yes, however, we say that light always has wave-like and particle-like tendencies. So it's not just under certain experimental conditions, that's under all experimental conditions. So that's technically a false statement. So that's not what we learned from the photoelectric effect. And then the energy of an object is proportional to its mass. So, what equation is that? I don't think there is no equation that relates energy directly to mass. We have the de Broglie wavelength, which is wavelength is equal to h divided by mass times velocity, which you can then use to solve for, right, use the wavelength in energy is equal to hc over lambda. Right, so you can find out if that is proportional, like technically it is, yeah, I guess. But that's not what we learned from the photoelectric effect. The photoelectric effect is that light has particle-like properties because we've shown a wave onto a bed, right, or a plane of something, an electron came off or a particle came off. And so the only way that that could happen is this if that wave was also a particle. So that's what we learned from 4. And so that's why 4 is going to be E. That it help your question, Andrea. Great. Okay, any other questions that we would like to see? Yep. Yep. So, right, this time we're talking about intermolecular forces. So we are talking about carbon dioxide, and we're talking about between molecules or right within the carbon dioxide molecules. So when we look at carbon dioxide, this is the structure that we come up with for carbon dioxide. We have a difference in electronegativity between carbon and oxygen. Which one is more electronegative, the oxygen or the carbon? Which way would our dipoles point? It's actually going to be the oxygen. So electronegativity increases as you go across the periodic table. So as you go from carbon to nitrogen to oxygen to fluorine, here electronegativity increases because fluorine is our most electronegative atom. And it goes, electronegativity increases as you go up the periodic table. So oxygen is actually going to be more electronegative. So we're going to point our dipoles out towards the oxygens because that means that our oxygens have a partial negative and our carbon has a partial positive charge. What is the shape of carbon dioxide? What is the shape of that structure? Great. Yep. So this is a linear molecule. So what happens to those dipoles? Do they superimpose? Do they cancel out? Perfect. Yep, they're going to cancel, right? Think about carbon dioxide being the center of a tug of war, and you have the same equal strength on both sides. If that's both pulling out, then that center point is not going to move. So this, right, they cancel out, therefore making your dipoles like null. And therefore, do we have any intermolecular forces within the molecule? Or I guess what is our overall polarity of the molecule, right? There's no intermolecular forces. So what's our overall polarity? Yep, zero or nonpolar. So if we have a nonpolar substance, what is the intermolecular force present in that molecule? Yep. So we only have London dispersion forces or London forces. So, right, we look at our answers. We don't have any hydrogen bonding because in order to have hydrogen bonding, we have to have H attached to a nitrogen, H attached to an oxygen, or H attached to a fluorine. So we can't have hydrogen bonding. It's not ionic bonding because we don't have full charges, right? An ion is something that either has a positive charge or a negative charge. We have partial positives and partial negatives, and we have non-metal ions. So this is not an ionic bond. This is a covalent bond. So it's not ionic. We do have London dispersion forces, and we do not have a metallic bonding because, right, these are two non-polar, or these are two non-metals. So this is not metallic bonding. So that narrows it down to covalent bonding and London dispersion forces. Covalent bonding is what is holding those molecules together. It is not an intermolecular force. That is like the big overarching thing that's holding them together. So since covalent bonding is not an intermolecular force, the only force present is London dispersion. And we know that based off of the structure and the polarity of the molecule. Alrighty. Does that help with 28? Any more questions on 28? Okay, someone asked for 27. So for 27, we have which of the following substances has the weakest intermolecular forces? So as you have, right, we know that London dispersion forces are the weakest, and that's from nonpolar molecules. Okay, so when we look at these structures, we have iodine like this. We have C C818. We have SiH4. We have carbon. And we have SbCl3. That might be the wrong structure for the last one, but you'll get the idea. So when we look at these 8 or 5 structures, what we need to look at is what forces are present and then how big are the molecules. So for I2, what's our strongest intermolecular force? What is the strongest intermolecular force of I2? Is there any difference in electronegativity, hydrogen bonding? What's going on here? Yep, this is just London dispersion forces. What about C8H18? C88H18. H18. What's going on with that one, with B? What forces are present here? So Alan, we're not gonna have hydrogen bonding here, because in order to have hydrogen bonding, we need to have a nitrogen, oxygen, or fluorine directly bonded to a hydrogen. So carbon and hydrogen are close enough in electronegativity that there is no difference there. So it's considered a nonpolar bond. So if all of those bonds are nonpolar, what does what forces are present there instead? Yep, perfect. This one's also London dispersion. What about SiH4? Yep, this is also LDF. What about D with an extra OH group? What can that do? This one can hydrogen bond because here we have the OH group bonded. And then what about SbCl3? What can that do? Yep, this is dipole-dipole. So looking at these 5 molecules, which ones can we get rid of immediately, right? Which ones can we get rid of? And why can we get rid of them? Yep, we can get rid of D, right? That has hydrogen bonding, and we can get rid of E because that has dipole-dipole. We know that London dispersion are our weakest, so we need to narrow it down to the 3 that only have London dispersion forces. Right? D and E will also have London dispersion forces, but we will not, that's not our weakest force in them. Okay, so then how do we differentiate between A, B, and C? If they all have London dispersion forces, what contributes to London dispersion forces? What factors make a London dispersion force greater or weaker than the other, or stronger or weaker than the other? Yeah, perfect, right? The size is what's going to contribute to this. So iodine's very heavy, right? Iodine is 126. Um, hold on, let me stop my share and then restart. Sorry, I think my Zoom is auto updating on my iPad, so just give me a moment. I'll just keep explaining it while it's updating. So the size of the molecule is going to contribute to the London dispersion forces. Iodine's 126 grams per mole, and we have 2 of them. So we have 200, what is that, 252 grams per mole, right? That's a very heavy molecule. And it's also element number 53, which means that we have 106 electrons when there's 2 of them within the entire molecule, making that a lot of electrons that could potentially be on one side of the atom at one time, or a lot of electrons moving around, creating more London dispersion forces. Okay, so that's why, so iodine is going to be a pretty big molecule, and it's going to have pretty strong London dispersion forces. If we look at the periodic table, fluorine and chlorine are small enough where they're actually gas at room temperature. However, as you go down to bromine, because of the London dispersion forces, bromine's actually a liquid at room temperature, and then iodine is actually has such strong intermolecular forces, it's a solid at room temperature. So we can see that even though London dispersion forces are the only thing contributing to iodine's ability to hold itself together between molecules, they're strong enough to make it a solid, right? So that's going to be pretty strong, London dispersion forces. If we compare, so I tell you iodine's on it. C8H18 is very big, right? This is a very big molecule, right? This is like giant, right? Like a string bean, right? Whereas this silicon H4 is actually just like a pea size, right? So a pea comparison to a string bean, right? That's a big difference. When we have a dipole, it might be able to stretch across the entire string bean. In the case of the silicon, then it can only stretch across the length of a pea, right? So the length of that dipole is much longer or bigger than the length of the dipole for the pea or the silicon. So the size of the molecule and how heavy it is will also contribute to London dispersion forces. So um, C8H18 is going to be a molecule that has stronger London dispersion forces than something that's smaller, such as the silicon H4. So C is going to be your answer here. Okay, that's a long-winded explanation, but that's why C is the answer. Does that make sense? And does that help? Who asked that? Right, so the smaller the molecule, the weaker the intermolecular forces. Yep, are there any other questions on 27? Alrighty, 17. So which of the following species would you expect to have the largest radius? Okay, so what we need to know here is that when we have an ion, we have two things happening. So if we're looking at neon, right? Neon has 10 protons and it has 10 electrons. If we look at fluorine, this has, or we'll look at fluorine minus, this has 9 protons and 10 electrons. And if we look at sodium plus, we have 11 protons and we have 10 electrons. Oh, I'll write that backwards. So they all have the same electrons. And then Chris, yes, to your answer and or to your question in the chat. So when we look at ions here, they all have the same electrons. We call this isoelectronic. So what I want you to think about when you're looking at the size of an atom and it's the size of an ion is the buddy system. So if you have neon, here you have 10 dogs, right, that are all your electrons, and you have 10 owners holding onto a leash, right? So each owner has a buddy of a dog. They can all walk the dog together. When you have fluorine, you now only have 9 dog walkers, but you have 10 dogs. So your one person is going to have to do double duty on a dog. This makes it a little bit harder to walk, and it makes it harder to walk as a group because someone has to do more work. In the case of the sodium ion, you now have more dog walkers than you do dogs. And so that means that you can double up for a dog, right? Or you can, right, they just have a stronger hold on that dog because they have 2 people holding onto it, kind of thing, okay? If you have a stronger hold like you do on the sodium, that means you're going to hold those things or hold those electrons closer to the nucleus, right? The nucleus is more positively charged, is going to have more attraction to those 10 electrons than it will if it were 10 to 10 or if it were 9 to 10. If it's 9 to 10 like fluorine, right, it doesn't have as strong as an attraction because there's less positive charge than negative charge. So that that electron cloud is going to expand out a bit. So your negatively charged anions, these get bigger, and your cations get smaller in comparison to their original atom size. Okay, so when we look at the when we look at our choices here, we are all looking at things. We have phosphorus. We're just looking at the periodic table. We have phosphorus, sulfur, sodium, selenium, and we have calcium. I'm sorry. And then calcium is down here. Calcium. Okay, so that's what it looks like on the periodic table. When we go from sodium to calcium, or we go a period down, right, we have our nucleus and we have various energy levels, right? And they all gain a circle around it. So as you go from sodium to calcium, you're gaining a whole other ring around that atom, increasing its size, right? So we already know that calcium would have a larger radius than sodium because it has a whole extra energy level. Sodium plus here is actually going to have one less energy level because it's getting rid of its electrons, and calcium plus has minus an energy level because it's getting rid of its electrons. So we already know that those are going to be even smaller than what we expected them to be. So your cations will never have the smallest ratio radius if there's anions in presence as well. For phosphorus, we know that between phosphorus and sulfur, these are next to each other on the periodic table. If sulfur has 2 more electrons, that means that it has 2 more electrons in comparison to its original number of protons, increasing its size. And so since it's going to increase its size, it's going to be bigger than phosphorus. So we can get rid of phosphorus. But then as we look between sulfur and selenium, we know that these two are both 2 minus. They're both bigger than the original atom that they started with if they were not an anion. But selenium is going to have one extra energy level in comparison to sulfur. So since we have the extra energy level, we get a little bit bigger in terms of our atom. And so selenium is going to be our largest atom. Does that help, Aiden, with your question there?
So it's going to be the one with the most amount of energy levels.
Yeah,
In
most amount of electrons and most amount of energy levels will always be our biggest.
and okay, that's for any question, right? Not just for this one.
Yeah, yep.
Okay, that'll work. Thank you.
Right, when we look at, right, the fluorine, neon, and sodium that I showed you, right, they all have the same number of electrons here. However, right, and they all have the same number of energy levels because they're all isoelectronic. They all look like neon, right? So your ratio of protons to electrons, this one here is 0.9 to 10. This one is 10 to 10, and this one is 11 to 10. So the smallest ratio of protons to electrons will be your biggest one. In case something like that pops up. Should we always assume that cations have a larger radius, even though the cation element? So if you're just looking at elements directly on the periodic table, right? If we're just looking at the periodic table here, right? This side, right? These metals here are going to be bigger than its respective atom on the same period in the same row. So, right, electronegativity, or I'm sorry, atomic radius decreases as you go across the periodic table. So just looking at elements directly off the periodic table, lithium will be bigger than fluorine because they are in the same period and atomic radius decreases. However, if we were to look at sodium, right, making it an cation, it now has the same number of energy levels as fluorine, or as neon, right? In that case, if it were just to look like a noble gas. Um, but because it has one less electron, then we know that it's going to be smaller. The anions are going to be bigger. Does that answer your question, Emily? Okay, great. Any other questions on periodic trends or like cation anion race or not race, radius? Yep, someone asked for 24 and 21, so I'm going to do those, then I'll do 16. Yes, Chris. Atomic radius decreases as you go up the periodic table, so atomic radius increases as you go down the periodic table. Okay. 21. Which of which molecule or ion is not planar? Alrighty, so the things you have to do for this one is you have to draw each of your structures. So, when we look at all of these, you would have to take the time in order to draw all of your structures. I will draw them for you. Okay, so here are your three structures here, or I'm sorry, five structures here. So when you look at each of your structures, does anyone know what the CO3 2- structure is? What is the shape of that molecule? Yep, this is trigonal planar, right? And planar is in the name, so you should know that that one is not going to be the answer, right? Planar sits flat in the plane. Right, that's the same thing for Cl2, Cc, Cl2. B here, right? We see that trigonal planar. These are both trigonal planar. So since right, both carbons have a trigonal planar shape, the whole thing will be planar. That's the same for E as well. So B and E can be rid of. I think that's the shape for HN. Math real quick. 10, 12. 1, 2. I think that's right. I don't know. The HN and H. Let me just look that up because I forget. Sorry. This is This is that. This is that structure here, the HNNH. This one will look like this, oh brother. In terms of it being in its actual orientation. So when you look at each of these ends here, this is actually going to be technically bent, and this will be technically bent. But because that they are both bent, you can make it so that it lays flat on the plane. So you think this will still be a planar molecule, even though it's like bent and bent this way. It is still only a 3-electron domain. So bent on the plane is just like right this here. You can still lay that flat on the page. So that will still be planar. So the only one here that is not planar is going to be H3O plus, and that's because this is a tetrahedral electron domain. So its molecular geometry is trigonal pyramidal. And I think we talked about shapes. Was it right after spring break? I think it was right after spring break. Maybe right before. What week is it? I think it was right after spring break. And right, so I always think of trigonal or of tetrahedral as a tripod with a phone on it. So if you think of your central atom as like the connector to the feet, and then like if you were where you would hang your phone on it, that's your central atom. Your phone would be like the top atom, and then your 3 feet of your tripod are the other 3 molecules uh around the central atom. So your H's here are like your feet of your tripod. Your tripod can't lay flat on the ground, right? It sticks up and it points out of the plane. So H3O plus is a 3-dimensional object, and therefore it's not going to be planar. All right, does that help with 21? Okay. And then for 24, we have which of the following molecules is polar? So again, you would like to write all the structures for this one. So when you're talking about polarity, you want to look for something that has a lone pair on its central atom. Technically, the only thing here that has a lone pair is this nitrogen F3. Everything else is symmetrical, and so therefore will be nonpolar. So NF3 will be your only polar molecule out of the 5. That's a great question. So if we have CF F, H, H, right? The way I drew this looks like we would have dipoles pointing out towards the fluorines here. However, this is not actually what this molecule looks like. What is the electron domain, or what's the shape of this molecule of CF2H2? Good, right? This is tetrahedral. So if something is tetrahedral, right, we have now a 3-dimensional shape that we're working with. So it's not actually planar and on the plane. It's actually something that looks like this, where you have the fluorine coming out of the page or the fluorine going into the page, right? So think of your tripod. 2 of the feet are fluorine, 1 of the feet is a hydrogen. So now our dipoles are going to point out towards our fluorines. And so what kind of molecule do we have? Do we have a polar or nonpolar? Polar or nonpolar bond? Yep, we have a polar molecule. So what intermolecular forces do we have? Good, we have dipole-dipole intermolecular forces. Why does boron not get a lone pair? Boron is one of our exceptions that is happy with 6 electrons. And that's just because it's a small element. It doesn't have many electrons to begin with. So that's one of the exceptions that it's happy with only 6, so it doesn't get a lone pair. Any other questions on 21 or 24 before we move on? We said 16. Okay, so what is the ground state configuration of CO3 CO3 plus? So this is cobalt, and when we look at cobalt, it's going to be argon 4s2 3d7. When you are taking away electrons or making them an ion for a transition metal, you want to take away from your highest energy level first. Right, so if you were to arrange this in terms of increasing numbers, then this would be argon 3d7 4s2. 4s2 has a 4, that's a higher energy level, so we're going to take 2 electrons away from our 4s first. And then we're going to take 1 away from the d orbital of what's remaining. So we're left with argon 3d6, which would be C. That makes sense there. Great. And then you also just want to make sure that you have the correct number of electrons as well. So cobalt is number 27. So if we have 27 minus 3, we need 24 electrons. So if we started off with, where were we? Right, we started off here, we had 9 valence electrons, minus 3, we want 6 valence electrons. For A, we only have 5. For B, we have 6. For C, we have 6. For D, we have 7. And for E, we have 7. So now you're in between 3D4 and 4s2 or 3D6. So that narrows it down there. And then you just need to remember that you need to remove your higher number first.
Is this the way that we always do ground state electron configuration?
What do you mean in terms of like
But
removing?
well, if we just had like a different atom,
Mhm.
like if we had bromine or fluorine or oxygen or whatever else, um, with like a 3 plus, with like a plus or a minus, we still follow the same thing of removing your highest energy level and then adding, I mean, removing 1 from your D, from your highest D orbital.
Yes. Yep. So,
Okay.
right, if you had something, so like anything that's not a transition element, um, no, I don't want to say that. I don't want to generalize.
Okay.
Yeah.
That works. That was
Yeah.
okay.
Yep. It just works the same way. So if you had something like bromine, right, that is, where is that? That's argon 4s2, 3d10, 4p5. So you're gonna, if you want to make bromine 7 plus, right, you want to remove the 4p5 first and then the 4s2 first, before you remove anything from the d orbital.
Okay. So in that case, we would remove the 4s2 completely and then remove, and then that would turn into 3D, not 4p5? Or do we remove the 4p5 also?
Nope, so you're gonna remove you want to remove your highest number first, and then your, I'm gonna call it your greatest letter. But right, like
Okay.
S is your lowest energy level, and then P,
Okay.
or lowest orbital, P is your next DF. So you want to remove it as FDPS. So
Okay.
bromine plus would be argon 4s2, 3d10, 4p4, right? You're going to remove from that 4p first.
Okay.
Does that make sense?
Yes, I believe so.
Okay. All right, so eventually bromine 2 plus is argon 4s2, 3d10, 4p3.
Okay.
Bromine 5 plus is argon 4s2, 3d10. That's it.
Okay. That works.
Okay. Why does 3D sometimes go before the 4s? In what sense? Like when you're like in the question where 3D 4 4s2. Yep. So, based off of the periodic table, right, you're going to fill the 4s before you fill the 3D. So when I write it 4s2, 3d10, that's just because I filled the 4s first before I filled the 3D. Right, I'm just reading it left to right. It doesn't matter how you write it, when it comes to here. They just rearranged this based off of the highest energy level. So they put all the threes first because that's lower energy level than the fourth energy level. As long as it is outside of the argon brackets, you're good to go. So Andrea, you're gonna fill what is not full yet. So, right, if you have bromine, we said that was argon 4s2, 3d10, 4p5, right? We have a 4s orbital that's full. We have a 3d orbital that's full. And then we have a 3p orbital that has one empty. So to make this bromine minus, this is now argon 4s2, 3d10, 4p6. You have to fill um what's empty. Chris, can you explain your question a little bit more, please?
So if like for question 16, it flipped the 3D 4S. So I'm saying
Yep.
if it had the P also, would the P go first?
So the P, right, if we were going to put bromine in here, it would be argon 3d10, 4s2, 4p5. That's how it would look in the question.
Okay, thank you.
Yep. Andrea, does that answer your question for making it negative? Great. Okay, any other questions on 16 or electron configurations? Okay, we asked for 14. So the change in energy for which the following process C's corresponds to is the first ionization energy of beryllium. So in order to ionize something, ionization has to occur in the gaseous state. Okay, so it has to be a gas in order for it to remove an electron, or to put an electron on. So that gets rid of B and C and E. And then we know that the first ionization energy means that we are only removing the first electron, right? One electron. So we're going from beryllium to beryllium plus, right? Because we're removing an electron and that's negative. So we're going to be producing an electron in the gaseous stage. So it's going to be A. This would be the first two ionization energies. Yep, the result will always be a gas as well. Yep. Yeah, if something's going through ionization, you're only changing the charge of the atom. You're not changing if it's solid or liquid or gas.
So it will
Okay.
always be, I have a question. So when you mean the ionization happens in the gaseous stage, is that always, that's going to be always true? And so is that talking about the BE plus G or the BEG part for
Uh,
the
both of
ion?
them.
Okay,
But
so it should always be a G there.
it should always
No,
be gas. Yep.
okay, okay. Even if we had like nitrogen or carbon or sodium,
Yes.
then it will
Yep.
always be a G there for
Yes.
both of them.
For both of them. Yep.
Okay, perfect.
Yeah, it has to, you have to like put energy into the atom in order to make it gaseous, remove its electron, and then it can return back to whatever state it needs to. But the process of ionizing something has to be in the gaseous phase. So even if you're making something negative, right, we made something positive here. If you're making something negative, so bromine going to bromine minus, both of these have to be in the gaseous phase, and then your electron's going to be on this side. And like sodium, right? Sodium starts off as a solid. So your ionization for sodium is sodium gas going to Na gas plus electron. And then we had 12. If the electron could have a third spin state, that is 1/2 minus 1/2 and 0, what would the ground state electron configuration be for carbon? So what you want to do first is write the ground state electron configuration as is. So carbon here is 1s2, 2s2, 2p2. So now you have 6 total electrons. You now just have 3 spin states. So instead of only 2 electrons being able to fit the s orbital, you can now have 3 electrons, right? Because we only could have originally up and down. But now we have up, down, neutral. So as we fill this up, carbon now becomes 1s3, because now we have 3 electrons that can fill it, 2s3, because now the s orbital can hold 3 electrons instead of 2 electrons. So that's why this is going to be C. We never reach the p orbital if the case of an up, down, and neutral. Does that make sense for 12? Okay. And then question 13, we have an atom of which of the following elements has the smallest atomic radius? So looking at the periodic table, we have, where's rubidium? So Rb is down here, chlorine's up here, magnesium is in the same as this one, silicone is here, and arsenic is here. Right, so I kind of try to draw that based off of the elements. So your smallest atomic radius, we know that it decreases as we go across the periodic table and increases as we go down. So if we go across, we know that our biggest is going to be rubidium, argon, right? Those have 2 or 1 extra energy levels as we go down the periodic table. So those are going to be off the table first. Then we have to look at magnesium, silicone, and chlorine because those are all in the same period. And so oh, sorry. Those are all going to be in the same period, so we have to look at those 3 going across the periodic table. And as the atomic radius goes down, the farthest right we get, so chlorine will be your smallest atom. Yep. Okay. Okay, so subshells here, this is L as your quantum number. So when n is equal to 6, L can equal 5, 4, 3, 2, 1, or 0. So you have 6 total options for subshells when n is equal to 6. So that's why that's going to be that. Orbitals is m sub L. So just pay attention to what options are available given the constraints that you have. Which principle is violated following the orbital diagram, right? So here we have 2 upstate electrons. This can't happen. And the Pauli exclusion principle tells us that spins are opposite. So that is what rule is going to be violated there. And then for 11, we have which of the following may represent an excited state electron configuration for a cobalt atom. We said cobalt was argon 3d7 4s2. So again, we need 9 total electrons. This one only has 6, this one has 8, this one has 9, this one has 7, this one has 9. So you can get rid of A, B, and D right off the bat. And you need something that's going to go to a higher energy level. This is your ground state. So C is the only one that gives you an excited state. Okay. Are there any other questions in our last minute or so? Yep. So for 5, this is again just true or false statements. So I always like to either ask myself, can I prove it if it's true? Can I prove it if it's false? So the energy of an electron in an atom is quantized. Only specific energy values are possible. We know this to be true because of our various energy levels that we have, right? Those are all at specific energy levels. So this is true. The principal quantum number specifies each unique energy level. This is also true, right? This could be 1, 2, 3, 4, based off of the period in the periodic table. And then an electron transition from a lower energy level to a higher energy level results in an emission of a photon of light. We know this is going to be false because in order to go from a lower energy level to a higher energy level, we need to absorb. We need to absorb energy to go from low to high, and we emit from high to low. So 1 and 2 are your correct answers here. Of course. Alrighty. Well, it is 8 o'clock. I have to do a couple of things to get ready for the week. So, good luck tomorrow. I will be there to answer any of your questions that you may have. If you do have any questions in the meantime, before the exam, I will be checking my email as much as possible, in the next, hours or so. And then once I get the recording back, I'll post it. So it'll be up later tonight before I go to bed. So if you need to watch it again at any point. Good luck. Don't stay up too late. Make sure you eat breakfast. Make sure you set multiple alarms and make sure you actually sleep tonight. It is better to sleep than to cram. It's under the resources page on the homepage. It's that second button right next to the course schedule. Yep. Alrighty. Have a great night. Good luck studying. Good luck tomorrow. Make sure you go to bed. That's the most important thing to do. Good luck. I believe in all of you. And great job. Yeah, you're so welcome. Thanks for coming. Good luck with everything.